We are now going to move on to a panel with Jeff from the Web3 Foundation, who does a lot of the research on Parachain developments, and Rob, who leads the implementation team at Parity and actually made Parachains work in practice. I'm Joe Petrowski. I lead technical integrations, and I'm going to be the moderator. So I think we'll bring Jeff and Rob up on stage now.
Hi. Yeah, thanks, Joe, and nice to see you, Joe and Jeff.
Yeah, so I think we want to kind of split this into two halves. So the first half is kind of how we got from the initial research into the current implementation, and then the second half will be kind of the future and what we're going from there. So to begin with, like about a year and a half ago, Jeff led a team who put out this paper on availability and validity. And this scheme has changed quite a bit as we've implemented it. Jeff, do you want to start out by giving an overview of kind of how you went about designing a lot of the availability and validity stuff? And then after that, we can get into a little bit how it evolved and changed.
Let's see. Yeah. So so we had a number of ideas here. So we in the end, we got a bunch of the ideas from sort of from the Ethereum ecosystem. And there was this idea of using erasure coding, but a number of ideas around this kind of sort of how do you optimize sharding was never really were never really formalized very much. And so so sort of towards the end of 2019, we had a bunch of ideas, and we had found some other cool ideas. And towards the end of 2019, I decided we really need to formalize, come up with a much more precise method. And usually the way we actually do design sort of complicated protocols here is we sort of try, or at least me, I try and write down what all of the possible design choices are and kind of start scratching them off. And so I hadn't actually done that yet for the Parachain stuff. So towards the end of 2019, and then through early 2000, towards the end of 2018, and then through early 2019, I pushed hard on that. Sorry, I'm getting off by a year. Anyway, and then in early 2020, I wrote down a design that was supposed to be a lot more precise. And then when I brought it back to people, we noticed that we started noticing some problems. And so then there was this trick I came up with, which was called two-phase. We call it two-phase inclusion, and it essentially means that the parachain the relay chain has to know about a block. Some validator has to say the block is valid before we start even working on it. And then after that, we start doing the erasure coding stuff, and then we do the real work on checking it. And the point of this, there's a number of benefits of this, but one of the ones is really that since somebody has some real skin in the game, it limits the amount of times you can try. And this gives us this ability to have something that essentially to attack the thing you would. Basically, we can make arguments that by gambler's ruin, you're going to screw yourself if you try and attack it, which is not the kind of, while it is not like the sort of cryptographic security that you get, it is a kind of distributed systems security, which is perfectly reasonable. And anyway, yeah.
Yeah, so do you want to actually discuss some of the availability challenges and what some of these attacks actually look like? Because I think it's a bit abstract for somebody who might be new to sharding, that actually, we have 1,000 validators, and when you want to include one of these parachain blocks, you actually have to send out chunks to all of them. So there's some kind of expense and complexity in networking and storage and kind of making everybody deal with these messages. So you want to actually make sure that they're valid messages and there for a reason.
Yeah, so erasure coding is quite old. There's many different types of erasure coding, but normally when you're doing cryptography, you use something related to something based on Lagrange interpolation or Reed-Solomon codes or something similar to this. And the reason is because it gives you a very sharp threshold, so we can say that from any, you know, 1/3 of the from any 1/3 of the pieces, you can recover the whole thing. So okay, so what do we do? We have this parachain block, and which we call a candidate, and we have, you know, 3 f+1 validators, and so we literally erasure code this thing into 3 f+1 pieces, such that from any f+1 you can recover. So this means that from anything slightly more than a third, you can reconstruct the original block. And this is a, you know, these are very, the mathematics is quite old. It turns out actually to make it fast with the numbers of validators we had to go and find some actually relatively recent papers on optimizing this stuff. Because we needed, and so that was one thing we did even this year was optimize the hell out of the erasure coding, and that it runs like 400 times faster now, and asymptotically it's actually faster. It goes from an O(n) squared algorithm to an O(n) log n algorithm, and so this is this sort of brings it into something where it's no longer like a really heavy part of the computation, though we can probably do a little bit better on that, but later. So that was one bit of work that happened very recently, and much more recently than it would have been nicer if it had happened longer ago. But
so turning all this research into code, that's I think we have some latency here. So turning all this research into code is like a whole other challenge. Like you can have all these papers and design. So Rob, do you want to talk about kind of like, we kicked off Rococo mid last year. And do you want to talk about like the start of trying to implement this protocol and some of the challenges you ran into early on?
Yeah, sure. We've been working on, I guess, implementing parachains. I'd say the first draft was something like late 2018, or at least the first code committed to it. But like, I think we really had a first draft, what I was calling the V0 protocol, in mid 2019. And you know, in those first years, we were focusing a lot more on like the Babe and Grandpa consensus protocols, like just block authoring, block finalization. So we hadn't really been looking too hard into the actual parachain stuff, and the research on that was a lot more complex. So that had a lot of time to develop. But from that period of, I guess, mid to late 2019 to early 2020, things were fluctuating a lot, as Jeff mentioned, because the research team was really trying to nail down that protocol for like things like availability, making sure that parachain blocks are still around so that other people can check them, and for like the security, the extra checking. I think it has been like pretty difficult to implement all of that research. Like I think a good rule of thumb when you're building any type of system, but I'm using it here to talk about coding, is like every extra bit of complexity you add to a system adds exponentially to the time it takes to create that system. And I think that applies very much so with code, because once you get a certain amount of code, it's really hard to add more stuff, because it's always going to cascade through and start to break some of the stuff that you added before. So it's really important, I'd say, to have like a good design and a good plan. When we were more like iterating in this prototype phase, we definitely did a lot of back and forth on the research. But what we've done in 2020 was really focus down on that implementer's guide to iterate faster there than in code, because we didn't actually have to produce like tests or something that would be accepted by a code compiler. We could just have like this testing ground where I could have a call with Jeff and Al and read, you know, the papers, the draft of papers that they were producing, and then write a page saying, okay, this is how we're going to write the code, but not actually write it yet. So that would save a couple of weeks, and then I could split that work up among like, you know, many different developers. So I think it's really important when you build a system like this to be to have a really good plan and have a modular system where you can add and isolate specific components of code so that you can reason about things as small packages as opposed to the entire system, because that's just too much for one mind to handle.
Yeah, and the kind of like as Jeff was saying, there were a lot of changes, like needing a whole new erasure coding system. So
that was relatively modular.
Yeah, but that's, I guess, the advantage of making it modular is that it doesn't trickle down too much.
Yeah, there's a lot of there's a number of complexities in the protocol. I mean, we had to do a lot of triage and sort of what really matters and what doesn't. So there's more stuff we want out of everything here, but what we have now works and is when we will, essentially we should be able to get fewer more sort of need fewer validators per parachain as we tweak some other things. But yeah, one of the other things that happens is that the first time you write something, you don't see all of the different the actual layers you want are going to want, and that actually is a really slow process, even for stuff that's really well understood. It takes a while to emerge when somebody starts implementing something. So it doesn't make sense to rush everything out right at the beginning. It makes sense to sort of like keep the other ideas you want around sort of on the and play with them in your head, which is even faster than playing with them in English, and then to see how they'll fit in, and how we can sort of fit in and optimize things later.
Yeah, there's going to be like a lot of like more stuff rolling out. Like we're basically doing something that's gonna work, and like obviously like when you're iterating in your mind or on paper, like you can write a paragraph of text that would take somebody years to execute. So we have like quite a few of those paragraphs lying around to just get around to and implement and just keep adding those features.
Yeah. So yeah, go ahead, Jeff.
Yeah, maybe I'll save it for later. Go ahead, continue.
Yeah, so I was going to say that kind of brings us to the state we are now, where we see the shell parachain on Kusama, and we've seen, I think, 15 parachains on Rococo, but we're seeing like 12-second block times. Things are a little bit slow on Kusama, so we're trying to work through that. What does what are the key challenges for parachains in the very short term, as far as like getting these up to like a 6-second block time and trying to onboard more of them to Kusama?
I think it all boils down to networking ultimately. Like I think it's cool that Kusama has 900 validators, and those are just like random people who own some KSM and are staking worldwide, and they run a node that falls into sync. It's cool. It's probably one of the biggest validator sets out there for any public blockchain. But when you're adding something as complex in networking as parachains are, like it's bound to be a lot of load. Like we had Rococo up to the same parameters before, but it's still not quite the same as those machines being run by like various people all over the world. So the main challenge is just going to be getting that networking code like running as smoothly as possible. We take a lot of considerations when we're writing the networking code to be like really spam resilient and so on. So that's stuff that when nobody's misbehaving, you don't really notice that it's there, but then once people start misbehaving, you're really going to be glad that you have those defense mechanisms.
Kusama brings a lot. I mean, it's really valuable to have a network that is that is much more heterogeneous than a test net would be, because we sort of it exposes more of the problems. But one of the things that we are going to run into is the fact that validator operators probably weren't. There's no way they could have been prepared for sort of the, as we start to add more and more parachains, there is going to be more computational load, and so we'll just see how that we'll just have to grow with how that impacts things, and that'll be a gradual learning process.
Well, that's what Kusama's for, right?
Yeah, so maybe if that goes reasonably well on Kusama, then presumably we'll actually start being able to, before it goes on Polkadot, hopefully we'll even be able to write down sort of, here's what you should really have as a Polkadot validator. This is kind of the load we're seeing and stuff like that.
Yeah, so kind of looking at the roadmap over.
It's going to add up.
Sorry, go ahead.
Like computation is definitely going to add up, because the way that we have it set up is like we have. Jeff alluded to this before, but like validators are sort of like supposed to acknowledge a block and put their stake behind it before the others start to look at it, and then you have a bunch of other validators like self-selecting to do checks. And more parachains you have, the more computation you do, although it's supposed to grow slower than the number of parachains, so that's why it's actually scalable, unlike just having more blockchains. But yeah, you're probably gonna have to be executing probably tens of blocks per second as a validator. Yeah,
so Jeff alluded to this, the two-phase inclusion. Do you want to kind of dive in a little bit more into that process of how a parachain block actually gets validated and included?
Sure, and this is something you can actually see in action on like the Kusama UI. If you go on the Parachains page there, you can see that like there's sort of this tick-tock effect of backed included, and what's happening there is that we have like backing as sort of an initial sign-off by a group of validators that have been randomly assigned to the parachain. So they'll say like Alice, Bob, and Charlie are assigned to the parachain, and then Alice and Bob take a block for the parachain and say, yep, this is good. And that statement proves to others that like, one, it has been checked, and also if it turns out to be bad, that those two are putting their stake on the line, so it's incentive compatible. And then once that parachain block with those signatures by Alice and Bob gets submitted on chain, it's now Alice and Bob's responsibility to distribute like this data to all of the other validators, so all hundreds of other validators, and give them each sort of like a unique piece that they're supposed to have, and any 1/3 of those pieces can be used to reconstruct the entire data. And what that's about is making sure that like the data necessary to check that a block is valid, so it's like transactions and proofs of like the balances of the accounts in those transactions and things like that, are still around when like people want to go check them later. And that'll be useful.
Yeah, so like in this example, Alice
checking.
And Bob would be the ones who actually connected to the collators of the parachain.
Yes.
Yeah, that's right.
Yeah, essentially there's two commitments that are made by Alice and Bob. One is the commitment that they're claiming is correct, and the other commitment is by distributing the data.
Yeah, so kind of looking at like the next year of parachains on Polkadot and Kusama, we have this idea of parathreads, which actually you see in the UI now, because parachains actually need to register as a parathread before they can upgrade to a parachain. But we want to make these a lot more functional. So do you want to talk about kind of like the design and implementation and kind of what's remaining to actually make these feasible in practice?
Yeah, so parathreads are pretty much the same as just parachains. Like the main difference is about how they get scheduled. So like we sort of have the scheduler process, and that says, okay, if you're a parachain, you get scheduled every single block, right? You're just always scheduled. You have your slot and you're scheduled. The parathreads process is gonna be about changing that scheduler to allow like auctions for like, parathread collators to compete with each other for the option to write a block. And that's going to come with some networking changes on the collation side of things. So like when you're a parathread block author, making sure that the validators know that you're around and that you have a block ready to submit. So those are the two main challenges that I see, is like that scheduler, the auctions. I guess three main challenges: scheduler, auctions, and the networking changes.
Yeah, there were sort of two design options for parathreads, and we went with this one that has this auction. And the reason is it's more spam resilient for us, but it exposes the parathread to possibly, if for some reason they can't get their block in or something like this, then they could possibly lose resources. So we have to there will have to be a few little, like there may have to be some economic questions we revisit there in some detail, but the basic design of the auction thing, it's not exactly the simplest thing that we could have done, but it seems like it's the most resilient. It's fairly resilient for Polkadot, and assuming that it worked, that we can get the networking up to snuff and make it work, then it gives a good option.
How does some of the XCMP stuff work with parathreads? Because like you said, a parachain is scheduled for every block. So if people are sending it messages, it can kind of like clear that queue every block. Whereas a parathread, what if it doesn't execute for like 2 or 3 days and all these messages pile up? Like, how do you handle some of this stuff?
XCMP. So we're not going to let parathreads go for 2 or 3 days without running. They'll have to make a block every day. The XCMP is fine with long delays. So there's one of the changes. There's a technical change improvement that has to be done, but it's planned on sort of how far back a block can be based on in the relay chain. That also has to happen for parathreads. But anyway, so as far as with XCMP, it can deal with messages that are quite far in the past. The requirement that it has is that the receiver of XCMP needs to have been watching the relay chain gossip so that they can know who actually checked the block that sent them a message. So they have to see an incoming message and know who actually sent it, which validators on the relay chain checked the block that sent them on another chain that sent them a message, and then that they can go and contact any of those validators. There won't be a lot of those validators right now. There's about 32. There won't be a lot of them, and in future it might be as low as 16 or something. But because they're selected, because the way in which they're selected, they're random enough that the message should be obtainable. So
there's the tech considerations of like, how are you going to get the messages? What if those messages are sent a long time? And I think what a lot of Jeff was referring to right now, correct me if I'm wrong, Jeff, but that was about like the off-chain XCMP stuff, as opposed to the on-chain where the messages are, which is what's implemented right now. And then the other aspect for parathreads is probably about like fees. So, if there's a lot of messages piling up and those have to pay some execution cost to the block author, that creates an incentive for somebody to actually come in and author that block as a parathread. So I think with the appropriate configuration of a parathread's fees to the moment, it's always going to create an economic incentive for that back pressure to be alleviated.
Yeah, so after we add parathreads, we've talked a lot about like offloading some of the core functionality from the relay chain into parachains, which enables further scalability and this idea of like nested relay chains. Do you want to talk about like why that's necessary to take some of this core functionality off the relay chain in order to enable bigger scalability targets?
It's easy. It'll be easier to have multiple. It's less nested relay chains. There may be some dominant one in some sense, but I prefer not to think of it as nested. I prefer to think of it as just relay chain shards. So in some sense, the sharding mechanism for that is actually simpler than what we've done already. But yeah, it changes some things. I don't think we should be pushing ahead we should be doing that. I don't think we'll want to do that probably to get above 3,000 validators or something like this. So I'm not sure how quickly that will happen. But I also don't want to tell people that they need to be rushing to implement that. I think we should try and do it well, like do the get as much off of the relay chain as possible, make the relay chain as simple as possible before we do that. Or that would be my preference. I think that's going to be the least work for the devs.
Like right now, the staking and elections modules and sometimes some of the governance stuff can be quite heavy, like impose a lot of load on the relay chain. And anything that happens on the relay chain, every validator of the relay chain needs to be executing. So you won't, as opposed to like stuff that's happening on parachains, where by design it's just a subset of the validators that are checking it, which is where we get our scalability from. You don't want you want as few things happening on every validator's machine as possible. So I think it will be quite difficult to extract some of the things like staking and governance safely, because there are certain failure modes in Polkadot where chains might be prevented from including blocks when they're being sort of analyzed in the dispute resolution mechanism and things like that. And then you might not be able to get the slashing transaction through. You might not be able to get the validator set update transaction through, and things like that are going to kind of be some more
slashing and governance. I would probably
tricky challenges. Yeah. But I don't view that as particularly urgent either. Like we're probably going to be able to optimize much more on just like on the node side of how we execute parachains and like how we process network messages to get more scalability and more parachains before we really run into that as an issue.
Yeah, we can. I mean, I think our goal should be, which it may not be reachable, but our goal should be to sort of reach parity where we have one parachain per validator. That may not be possible, but we should sort of understand the limits that we're hitting there, and then push in these other directions. And that means, and in particular, we would be good to really have our networking, like to know that we've made enough progress on the networking side and other things first.
Yeah, so a minute ago you said 3,000 validators, which means 3,000 parachains. Rob, as the implementer, how do you feel about hitting a target like that?
Not for a little while, that's for sure. I think I'd be quite happy if the code after a good round of optimization is running 80 to 100 parachains. That should be more than enough for the community as well.
Yeah, ultimately at some point we're gonna start hitting, I mean, what's likely to happen is we're gonna start running out of users at some point, and then we have to start convincing more people to use it. I mean, it'll kind of go in these spurts, and then I guess.
Yeah, it's kind of a challenge for like Polkadot's governance to handle of, what is the long tail of the auction schedule going to look like? Because like at some point, if all the tech stuff goes well, you're going to have the ability to run way more parachains than there maybe is even demand for specific parachains. And you don't want that to get filled up with junk for 2 years indefinitely while the community catches up. So there's going to be this sort of back and forth thing going on.
Yeah, well, I think time-wise, that brings us to just about 30 minutes. And actually, the next talk by Sean is about auctions and slots and crowd loans. So I think that's a good place to leave it.